everyone. I hope everyone is listening clear and loud. Thank you, Marco, and we are starting our weather briefing today. As usual, it is always a pleasure to know where those who join this session come from. So could you please use the drawing toolbar and put a mark in the place where you are? Okay. Mainly in the, oh wow, we have someone from the Eastern Europe, not quite. Okay, so lots of Asia, wow, lots of participants, so let's move on. Thank you so much. So these past days we had a stationary weather pattern and over Europe, and on the east side of Europe the cold air spread south, reaching the Mediterranean Sea, and on the west side deep cyclones over the Atlantic are helping pump the warm air to very high latitudes. So this stationary high pressure system over Central Europe is gradually weakening, and by the end of this week, a more unsettled regime will come. We had some record-breaking warmth for Northern and Western Europe. You see these records over United Kingdom. So spring weather in some places in Europe. But we also have some local severe weather in the east and southeast Europe, where cold air masses turn the area unstable. Also, this is the kind of events that we can expect it with a blocking situation. I mean, some unseasonably temperatures in both sides of the reach, with sometimes dry weather in the west and local and sometimes rain and local floods and severe weather in the east. But we also, I show here some pictures with some lenticular clouds over Croatia. So we also had some nice features that appear also in Europe. We also had some a borowind event over the Adriatic, very significant events. We had a windstorm in Malta and some floods in the Southeast Europe, as I mentioned. So this is the 6 UTC air mass RGB image with the mean sea level pressure overlaid, and it still shows the cyclones over the Atlantic and with frontal cloudiness, and cold air masses over Eastern Europe with some. So we have the deep cyclones over the Atlantic with frontal cloudiness, but also over Eastern Europe we had some loss and this trough over here. That's this one. Sorry, this trough over here, over eastern part of Europe, that will bring some winds and some rain. Over the Central Europe, this area here over France, there is a stable air mass and this cloud-free area with low land surface temperatures appear greenish in the air mass RGB, in this RGB. This stable air mass is not so good for the dispersion of the air pollution. So I listened to the media today, and it seems that Madrid and Paris have already some problems with the pollution, and they have to control the traffic for today and maybe the next days if this situation persists. Another interesting thing is this high gradient over here. So there is a windstorm that is approaching Norway. Later I will show you some ice skate data that show the high winds over the North Sea. Let's clear this. Look at this area over here with this highly cloudiness over Adriatic Sea. In this case, they form along the jet stream axis and at the anticyclonic side of the jet in a stable layer, of course. So with the upper levels, we have here the 300 hectopascal height, and it's very clear the blocking pattern, and with the omega shape, you can see over here. So this is very well seen with these high levels to see the omega shape over Europe. And also with this jet stream, or at least the isotax at 300 hectopascal, also we can see the high amplitude, almost stationary waves that we can see over here. You know, these high amplitude waves, and they soon will soon change to a more zonal flow that came here from the west. So this will change the weather in the next few days. Also, I want to mention also, just to clear this, just to mention some interesting areas with, of course, we should somehow pay attention. The reddish color, you know, some of you already know, the reddish color indicates areas with the PV anomalies. Or dry descending air related to high potential vorticity. Do you think that there are areas we should pay attention to? You can use your mark to, yes, of course, this one. Yes. Of course, there, the first one, yeah, it's near Iberia, so we should monitor this area. Yeah, okay. Also this one here over the ocean. Yeah, not as much areas. Maybe during winter we usually have some interesting cases. We have over the Atlantic, but nothing so exciting about it. We also have some areas with turbulence that can disturb the flights. Can you, I will clear these annotations. Can you show some areas that you think there can be some turbulence that can disturb the flights? Yes, yes, very well. Very well, yeah, perfect, yeah. Very good. Let's move on. So let us focus on these systems over the Atlantic and try to find the fronts. I show here the thermal front parameter and the equivalent potential temperature at 850. And these are some of the key parameters that help us to find fronts and identify which type. So you can see very well here, another one here, and the warm advection, so the warm air moving north, also here. So some interesting frontal areas that we have here, the cold advection over here, and some occlusion also. So we have several systems over the Atlantic that has some frontal boundaries. Sometimes they seem quite straightforward, but when we see, for instance, the vertical cross sections, that is not so easy to identify and to see which type it's each front. But this is always the problem with the conceptual models. Not always the key parameters fit perfectly. So here it's the same region, and we have the temperature advection. So the blue areas are the cold advection, the red areas the warm advection. And I want you to, I'm not sure if you can see the observations well, but notice the dew point depression between the observations. So here and here and over here. This is the West Highland, the Flores Highland in Azores, and you see that there is a difference in the dew point depression, and Azores, the West Highland should be in cold air advection, but in fact, it's for Highland, it's not that cold. So it's still, somehow it's a warm air that is behind this frontal cloudiness. So it's quite difficult to know if we have here, for instance, two cold fronts, or maybe a cold front in warm advection. So it's difficult to find and to see each type of cold front, or what type of cold front we have here. So let's check this vertical cross section in the that is represented with by the green arrow. So we are going to see this area here, and we have the vertical cross section with the black lines that are equivalent potential temperature, and the red-blue lines are temperature advection. So the isotopes, the isotropic surface with the vertical spacing between isotropic surfaces is a measure of the dry static stability. So if the lines are closed lines, we have closed lines, we have a very stable layer. Look at this area over here. That is the tropopause, is a very, very stable layer. So the lines are very close together. But also over here. So this is a frontal zone. We have the isentropic surface very close together. To identify the front, we need to see if these lines are inclined. So we have like this, And in this case, we have the a forward inclined zone, which means is a warm front. Also, to see the warm front, we have the warm advection. We have here a maximum of warm advection that is related to the surface warm front zone, and a second one that is in the upper level frontal zone. So we have here some two maximums of warm advection, warm air advection. This could mean that we have here a warm front shield. Maybe not, but I think so. So let's move on to the cold front near Iberia. We have a cold front, another vertical cross section, and again we have the closed lines over here, that is the frontal zone, and also we have the inclined, backwards inclined zone, that means that is a cold front. Of course, here we have the warm advection here ahead of the front, and the cold advection behind the front. So this one is nice to identify the cold front here. This one is a cold front. So just to sum up, the vertical cross sections with isentropes, you look at the closed lines, and then if it's the inclined zone. If it is a forward inclined zone, is a warm front. If it is a backward inclined zone, is a cold front. Okay, let's move on. So another information from the from 6 UTC today, we have lots of high cirrus clouds, high cloudiness over the Atlantic. We also have some low cloudiness over here. Maybe change the color. So we have here some low cloudiness over the Atlantic, approaching the British Isles, but we also have several areas of high cloudiness over here and over here. Okay, so just to remember, so the cirrus clouds that are black, like here they are black in this area, is because none of the color beams is contributing. So in the red beam, the brightness temperature difference turns negative, so the contribution is near zero. The green beam is also near zero, so because the green beam is useful for the low cloudiness. And in the blue beam, it represents the cloud top temperature, has a small contribution because we have very cold tops. So in case of thick and cold ice clouds, the contribution is almost null, and we have the black. But if the ice clouds become thinner and are located over a warm surface like the sea, they turn into blue, like we have over here. Okay, so these red ones, so the high opaque clouds, are in dark red because despite it's almost zero, it's the only contribution we have in this area. So this is the red because of the small contribution of the red beam. You also have some interpretation of the right side, so you can find some other areas, and you can see this information in the quick guide from EUMeTrain webpage. Okay, so let's move on. I'm almost finishing this presentation. We have here some the windstorm that is approaching the North Sea. You can see some warnings over here, and also over here, these warnings are mostly from wind warnings. And you can see here the wind data from ASCAT. We have here some overlap passes, but you can see the reddish colors. They are the higher values of wind speed. So you can see several areas of 30 and 35 knots and higher also. So this area was, and this one here, and this one here, sorry. This was at 0 UTC today, but this area with high values of wind speed is approaching Norway, the northern countries, and we'll have some wind speeds, high wind speeds today and maybe tomorrow. Just to finish the last slide, we had some events with Levanter wind event in Gibraltar Strait. And you have also here some high values of wind speeds near 30 knots. And in this case, it was enough for the wave generation was enough to issue a yellow warning for south of Portugal, and high values of significant wave heights were detected by a buoy that is located here, this one here. And due to the coastline characteristics, the yellow warning is issued for 2 meter high, so not that much. It's not very high, 2 meters, but due to the characteristics of the south coast, we have to issue a yellow warning. And you can see that for almost 2 days, all the significant wave heights were above 2 meters. You can see here, and the winds and the waves, the direction of the waves were southeast waves, so according to the generation of the winds also from east and southeast. Okay, thank you. This is my last slide. Now, Bruno, the floor is yours.
So, good afternoon. I will show now some events that occurred during the last month. Here we have a big fire that occurred in Tuscany, Italy. Let me just and the smoke can be seen in the HRV cloud RGB. I know it's an almost impossible task without knowing Italy geography, but can someone see the smoke plume? I can tell you that it's a very small plume, and it's only visible over the Mediterranean Sea. Yes, correct. So I will clear all the pointers just for you to. Okay, so there it is. It's very small, so it's very difficult to see. And if you use during the nighttime the night microphysics RGB, it will be possible to identify the active fire, and we can zoom. We can zoom it so you see the. Let me just point it. You can see the dot. This dot here, and and it helps us identify the active fires. So it's very sensible, especially to the infrared 3.9. If there is some similar areas and we want to cast away our doubts, we can look at the infrared 3.9 channel as an isolated channel, and as you can see here, it's a very dark color, dark for identifying the temperatures over the pixels in this area here. So a forest fire can reach usually temperatures between 500 to 1,200 Kelvin, and sometimes even surpass these temperatures. And at these temperatures, there is a very strong emission in the middle infrared, so wavelengths between 3 and 5 micrometers. So they can be captured by the 3.9 channel, even if the fire area is smaller than the size of the pixel channel. So because of the strong sensitivity to the subpixel of the 3.9. Emission by fire strongly contrasts with non-burning background. There's a question here: is why in the 3.9 is dark for fire if the emission is strong? That might be confusing, but it was chosen to display the cold clouds in white and the hot land in dark. So looking at this image here, the night physics RGB, can you spot active fires anywhere in Europe? Any other spots? It's also a little bit, yes. There they are. So it would be easier if we had a bigger zoom, but yes, there you can see. And if you look at the 3.9, there's, although it's very small, but there is an indication of active fires in that zone over there. So also in this RGB we can see some snow. That's an easy question also. Can you point it out? It's the usual suspects, the Alps and the and the Pyrenees. Of course, there's also some eye-level clouds. Let me just some eye-level clouds. Do you see it? Some thin cirrus. Yes, mainly there. Yeah, and yes, of course, at the southeast of Italy. Yes, over Sardinia and Corsica. Yes, very well. And there's some beautiful atmospheric feature here, the Lee waves, and we can see them, yes, very well. We can see them perfectly in this RGB. So looking, so they formed, these Lee waves formed on the left side of the Dinaric Mountains, and they extended over the Adriatic Sea and over Italy. We had a high pressure system to the northwest of the mountain range, and an upper low at the southeast, and these two action centers provided the ingredients to a northeasterly flow to be formed, and it is perpendicular to the mountain range, causing this cloud formation. And here you can see with the 6.2 and the geopotential for 250 hectopascal, also the deepening here of the low. So also looking at last month, we had a dust storm over the Canary Islands, and using the HRV cloud RGB during the day, we have a big contrast between the dust clouds and the sea. So it's you can see it here and here. This high contrast is due to the higher reflectivity of the dust particles in comparison to the sea surface. And using the dust RGB, we can pinpoint the dust cloud in cloud-free regions in magenta. So you can see it here and here, and they have high contribution of the blue and red channels, and you can have observations during the nighttime. Although in this case they are difficult to observe because they are low-level dust clouds, and the large red contribution happens because of the long wave radiation from Earth's surface usually, and is stronger absorbed by the dust layer at 10.8 than at 12 micrometers, as you can see in the image. But this is mainly over land, so over the sea it's not the contrast is not so big, so high. Looking at two lows that were named and had an impact mainly in the Azores Islands. They are over here. This was in the 23rd of February, and they have high impact mainly in waves and winds, also in rain. And we could use some products from the nowcast SAFing, the SAF nowcasting, and we looked mainly at the convective rainfall intensity that helps estimate the precipitation rate of convective clouds, and it provides us forecasters the complementary information to other nowcasting SAF products and RGB satellite images in relation to rain and convection monitoring. We also use the RDT, and it provides us information about significant convective systems, how they are maturing, if they are getting triggered, if they are decaying, and the way they shift in the last hours. And here you can see the high impact of the depression, the low Kyllian in the Azores. Before this one, we had the Julia depression also affecting Azores. It was an explosive cyclogenesis. We had a difference in 24 hours of 44 hectopascal, and it continued to deepen, reaching a minimum value near 936 hectopascal in these days. We had here the intrusion of stratospheric air. Here, these were where the activity of the storm was the strongest, and it continued to evolve. And Azores are somewhere here, and it also had a high impact in the Azores. We also could follow it through the RDT, the rapid development thunderstorms produced from the nowcast SAF, and also through the convective rainfall intensity. It reached values very high for that area. And so, to sum up, we had here some wind, some waves, some snow, some hail, yes, and it affected Azores during this period. Thank you very much for listening.